Well, good morning, everybody. Good morning, Abby. Today is all about making it through till tomorrow. I don't know what it is about this year, but I am so thankful to have this weekend. It's just different this year. Anyway, we're gonna get there. Tomorrow, I get to smoke a turkey, and I have made the ultimate decision today. I am gonna bake an apple pie.
Ooh.
I have never done that before, but I am gonna bake an apple pie. My wife really badly wanted a Blue Raven pie, but it's just not gonna happen because I'm not gonna get out to Amity to go pick it up today. But I just decided I'm gonna bake an apple pie. Why not? I like to cook. I do all this stuff. Why not? So I'll let you know Monday how it all went, because I gotta go buy the stuff for it today. So anyway, that has nothing to do with physiology, but I thought you ought to know. So on Monday, I booked my flights to New York to go see Milo Rocket and Cody Danger.
His middle name's Rocket.
Yes.
That's so cute.
Yeah.
I love that.
I mean, they are going to be the duo. I mean, they're almost, they're superhero names. Cody Danger and Milo Rocket. Anyway, I've already noticed a little interaction between the brothers because Cody has totally claimed the little penguin that I sent Milo. At this point, Milo, I'm sure, doesn't care, but Cody has adopted it. So there you go. And in January, I just might even spend some time with my son and daughter. So if I have time after spoiling the kids. So anyway, just one other thing, in case any of you care, I have moved my ornithology lecture from the odd Monday, Wednesday, Friday time that sits right on top of OChem and biochem in the spring back to Tuesday, Thursday. It's traditional time. So I am still looking for a couple of students. The class is going to get taught, but everybody will feel a whole lot happier if I can put a couple more bodies in the chair. So if you know anybody who might be looking for a fun class, it's fun, right?
It's fun.
Yeah, there you go. If you're huh?
I said there are some things that are not fun with exams, but let's give it.
Yeah, but
but it's not like this class though, right?
No, nowhere near this fun.
So anyway, if you know anybody who might enjoy a little outdoor time in the spring, I'm looking really hard for a couple more bodies. So do you guys have any questions before we get started? I will get close to finishing topic 9 today. I don't think I'm going to finish it, but I'll just have a few slides left when we get back on Monday. Probably, and in fact, there isn't even probably about it. This afternoon, I will post a video for topic 10. It's a short video. It's one I recorded. I recorded a couple of years ago, but the content hasn't really changed. So I'll put that up. And then on Monday, come back, we will start topic 11, and that will be it for us. That will be what we get through. And then the following week, we'll be into oral reports. So, okay. Yes, Anita, I knew I could count on you.
Yeah, I was like throwing one up. I was like, what can I ask him this morning?
Yeah.
About when do you think you'll have the oral surgery reports graded?
As soon as I can get to them. It'll probably happen. It'll probably happen over the next 4 days sometime.
Okay.
Those don't really take me that long to grade. It's not like grading the rat reports. those take me a long time, but these won't take me too long to get through. I just got to find the time to sit down and do it. And, so that could very easily end up being like a Friday morning activity for me.
Okay, cool.
Well,
I was just wondering, so then we can have it before our next one is due. So then we can
yeah, well, I don't think the next one's due until next week sometime, right? Yeah, so I'll get it done during the break.
okay, cool. Thank you.
Anything else? All righty. Grace and Jasmine, can you hear me okay? I see a Jasmine thumbs up.
Yes.
Okay, and I hear a Grace yes. Okay. Sounds super. Okay. So let's do a little screen share here. But that's not what I want. I want. Yes, that's what I did. That there. I'm talking to myself, that just kind of happens. All right, I think this is the slide we left off on last time, right? Okay, so I just thought I would start here this morning, just to kind of capsulize where we left off. We were talking about how the loop of Henle works and how the loop of Henle is a counter current multiplier. Yes, not counter current exchange, but a counter current multiplier. Goodness, it's right there in red. So that was probably really hard to pick up. Anyway, so and the way this works is it works by creating a rather substantial salt gradient in the interstitial fluids around the loop, and quite frankly around the entire nephron. And so as filtrate moves down the descending arm of the loop of Henle, it encounters these huge salt gradients, and then water is going to flow out into the tissues surrounding the loop of Henle and eventually be picked up by capillaries to be carried off. As water moves out of the descending loop, the filtrate becomes more and more concentrated because the descending loop is not permeable to salt. Okay, there may be some passive movement of salt. Okay, because remember we said last time that because the osmotic concentration, when you get down to the hairpin turn down at the bottom of the loop, is equal to that of the interstitial fluids surrounding the loop, that they think that is a result of some passive movement of salt across those tissues. But then when the filtrate starts to move up the ascending arm of the loop of Henle, salt, particularly when we get to a thick portion of the arm up here, is actively transported by the sodium potassium ATPase out into the interstitial tissues. And so because salt is moving but water is not, because remember that the ascending arm is not permeable to water, salt is being pumped out. So now that remaining filtrate is becoming less and less concentrated. And so by the time we get to the top here, it's actually rather dilute. So it gets to about 100 milliosmoles up here before it enters the distal tubule. All right. And so also remember that the longer this loop, the more concentrated the fluids get as we move toward the bottom, and also the more salty the external fluids surrounding the loop get as well. Okay. Was that a good capsulization for you? All right. All right. So key to all of this working is that when water and some of the salt gets pumped out into those fluids surrounding the loop, that water and some of that salt has to be taken away. If the water just sits there, then those fluids are going to, number one, it's going to build up in volume, but it's also going to become more and more dilute, and that defeats the purpose of creating the gradients that pull the water out of the loop of Henle. And removal of removal of the water and some of the salt is the job of a group of capillaries that surround the loop of Henle that are called the vasa recta right here. Now, the vasa recta is another cleverly designed aspect of all of this because it comes off of the efferent arteriole that is coming out of the glomerulus. So remember, we've already filtered a lot of fluid out of the blood when it goes through the glomerulus. So the volume of blood that is in these capillaries, the afferent side of the vasa recta, is going to be lower, okay, than what it was when it went into the glomerulus, because we filtered all that stuff out of it. Okay, does that make sense? And that provides the room for it to pick up all this stuff and carry it away. All right, the vasa recta creates a countercurrent exchange mechanism. All right, common thing to happen here is to confuse the countercurrent multiplier that is created by the loop of Henle and the countercurrent exchange that is created by the interaction between the vasa recta and the loop of Henle. Okay, they are different. So remember that the countercurrent multiplier tends to amplify a gradient. The countercurrent exchange tends to maintain a gradient. That's the key distinction between the two. And so just by definition, a countercurrent exchange is the passive exchange of a substance or energy, because it could be something like heat, between two fluids flowing in opposite directions. All right. So here is kind of how it works. And we'll start with this diagram over here. It's very diagrammatic, very simplistic, but I think it illustrates how this works pretty well. So in the center here, we have the vasa recta, and you've got blood flowing. You've got blood flowing down one side and up the other. And on the outside here, we have superimposed the loop of Henle. Okay, so over here we have fluids flowing down, the hairpin turn here, and then fluids flowing back up. So as filtrate moves down the loop of Henle, okay, the blood is flowing in the opposite direction. Now the blood has picked up salt from the ascending, indirectly from the ascending arm of the loop of Henle, directly from the surrounding tissues here. So the fluid, the blood in the vasa recta has become very salty. Okay, this creates the gradient which pulls the water from the surrounding tissues into the capillaries that will allow it to carry it back into general circulation. Right? And then so this is countercurrent exchange between the descending arm of the loop here and the ascending portion of the vasa recta. We also have countercurrent exchange with regard to salt. The descending portion of the vasa recta, okay, is picking up salt from the ascending arm of the loop of Henle, because these fluids flowing in opposite direction are maintaining the salt gradient right here, because it's picking up salt in the from the fluids, dumping it into the blood right here. So it will maintain these gradients that are represented by the salt concentrations in the blood right here that allow for the water to be picked up as the blood is leaving the vasa recta. Does that kind of make sense? Everybody follow that pretty jumbled mash of words that I just threw out there? Okay. So anyway, this is a really, really amazing design. Okay. I mean, it's just incredible. So, you know, this is why creation is so great. Yeah.
Just to double check, on one side it's picking up salt and on the other side it's picking up water.
Yeah, this is very diagrammatic, okay? But that's in essence what's happening. Because when the blood comes into the vasa recta, it's at 300 milliosmoles. All right. So that's the standard osmotic concentration for most living things. Okay, but as it drops down into the cortex of or the medulla of the kidney, okay, it's experiencing all of that, all those salty fluids that are surrounding the loop, and so the salt is flowing in. It's flowing into the vasorector right here, and creating a salt gradient that will in turn pull water in. The water will follow it at that point. And because the blood and the blood in the vasorecta and the filtrate in the loop of Henle are flowing in opposite directions, it serves as a countercurrent exchange mechanism that maintains these gradients. Are we good with that? All right. So once the filtrate is through the loop of Henle, then it's going to enter the distal tubule and eventually the collecting duct. And as we mentioned previously, these are two structures that we generally tend to talk about together. And another thing that I want to point out from this diagram here, because it's relevant, particularly to the collecting duct, is that not only is the osmotic concentration of the fluids surrounding the loop of Henle influenced by a high salt concentration, but it's also influenced by urea. Okay, urea is osmotically active, but it's an organic molecule that when we get to the end of today or possibly on Wednesday, we will see actually serves as a type of molecule that we call an osmolite. It's an organic molecule that doesn't mess with proteins quite so much, although urea actually can mess with proteins, but it tends to be fairly inert with regard to interaction with a lot of other molecules in cells. Okay, and so having some small organic molecules that contribute to at least some of the osmotic concentration of these fluids is a good thing for cells. We'll talk about that a little bit later. And then in a moment, we'll look at how urea is actually cycled through the medulla of the kidney. In fact, we'll talk about it right now. So here is a nephron right here. So at the glomerulus, we are going to filter urea, and urea is going to travel into the proximal tubule, where half of the urea that's been filtered is going to be immediately reabsorbed, right? And so that half that remains in the filtrate is going to travel through the loop of Henle, and when we get down into the loop of Henle, that 50% that was reabsorbed is picked back up by the filtrate, so it moves back into the loop of Henle. So when the filtrate leaves the loop of Henle, it's got as much urea in it as was filtered, okay? Then when we get out into the proximal tubule and the collecting duct, about 30% of that is reabsorbed. So as the filtrate moves down through the collecting ducts, we're at about 70% of the urea, the total urea that was originally filtered at the glomerulus. And then just prior to leaving the collecting ducts, about 55% of the urea of the total urea that was originally filtered is reabsorbed, leaving 15% to be excreted. So, when your final urine is produced, it only has about 15% of the urea that was actually filtered in it. Now, this 55% that's reabsorbed here is what is used to replenish the urea in the loop of Henle. So this is why it's recycled. And then about 5% of that gets taken up in the vasorecta and taken back into circulation. Okay. And so this urea cycle here, keeps a relatively constant amount of urea in the medulla of the kidney to contribute to the increased osmolarity that's necessary to help water movement. Does that make sense to everybody?
Can you repeat the last thing that you said one more time?
This process of recycling the urea okay? Pulling it out of here and then just sticking it back into here. So we've got this continuous loop going on is allows the kidney to maintain a fairly constant urea concentration in the medulla of the kidney. And this urea contributes to the high osmolarity that that promotes water movement out of the various parts of the nephron.
Thank you.
Does that make sense, everybody? Are we good with it? All right. So the filtrate now is leaving the loop of Henle, going into the distal tubule and the collecting ducts. The distal tubule does continue to actively transport salt, so there's still some additional salt reclamation that's going to occur in the distal tubule. And then the filtrate's going to move into the collecting duct, which is permeable to water, but not permeable to salt. So we lose salt transport for the most part when we get into the collecting ducts. Now, when I say we lose salt transport, what I'm specifically meaning is these constant set in place mechanisms that are always transporting salt. So you don't have the sodium potassium ATPases that are just constantly reclaim it, because the collecting ducts, remember, as we've emphasized, are under hormonal control, and we can reclaim salt that way by modifying the membrane permeability through hormonal means. Okay. So in that sense, they can be made permeable to salt under the right conditions, but this is mostly for fine tuning the amount of salt that you're going to reclaim. Does that make sense? All right. So once the filtrate gets into the collecting duct, we are primarily into fine tuning mode for both salt and water, and the degree to which the collecting duct is going to be permeable to water is going to be a function of ADH, antidiuretic hormone, also called vasopressin. So how does that work? So when ADH concentration is high, then the membranes of the collecting duct, and specifically the luminal membranes of the collecting duct, become more permeable to water. Now, the basolateral membranes of the collecting duct are always permeable to water, but the luminal membranes, where you have to get the water from, become more permeable to water in the presence of ADH/vasopressin. So what happens here is that when vasopressin levels are increased, what's going to happen is the cells of the collecting duct are going to place these vesicles that contain aquaporin 2 proteins, okay, a type of water channel, into the luminal membrane. They retain these things in vesicles inside the cell, so they save them up, and when they need them, they're inserted into the membrane. When they don't need them, they're taken out of the membrane. To the best of my knowledge, this is the only water channel that is actively hormonally controlled in mammals. There may be another one that I'm not aware of now, but to the best of my knowledge, this is the only one that is hormonally controlled. All right. So as ADH levels increase, then the more aquaporin 2 proteins you're going to get stuck in these luminal membranes, the faster water reclamation, or the more water reclamation is going to occur. And then once water moves through these aquaporin 2 proteins that are on the luminal membrane, then they can travel through the cell and then be picked up in circulation. They will move through some additional aquaporin proteins, aquaporin 3s and aquaporin 4s that are on the basolateral membrane. And then once the water goes through there, they'll get into circulation and be returned to the body core. Questions about anything on this slide? Okay, so as ADH increases, so when ADH/vasopressin levels are high, then urine is going to be more concentrated because you are excreting less water while retaining a lot of the solutes that are in urine. All right, here's just a few flow charts that just kind of illustrate some of the physiological things that go on when water levels are high versus when water levels are low. And so we can just kind of walk through some of these flow charts here. So if you are drinking a lot of water, so, you know, you sat down and just downed a few liters of water right here, so you have excess water that's been ingested, then what happens is the osmolarity of your blood basically is going to decline. Okay. Another way to look at that is water concentration is going to go up. This is going to trigger the some osmoreceptors that are in the hypothalamus. And then this will result in a downregulation of ADH/vasopressin secretion. The result of this is your plasma levels of vasopressin are going to decline. The permeability of the collecting ducts to water is going to decline, and you're going to reabsorb less water, and more water is going to be excreted. So you will start producing some very dilute urine at this point, and a lot of urine at this point. Okay. The flip side of this, when plasma volume decreases, so you become dehydrated, then your blood pressure is going to go down, and this will trigger baroreceptors. So it refers to cardiovascular baroreceptors. Where are these? Test your brain.
Carotid sinus.
Okay, carotid sinus is one place. Where else? One other location.
Aortic arch.
Yeah, in the aortic arch. Yeah, so those are the two locations where you will primarily find these. This will trigger an upregulation of ADH/vasopressin secretion. So plasma vasopressin is going to increase. And then the collecting ducts will increase in their permeability to water. They'll be inserting all those aquaporin 2 proteins into that luminal membrane. Water reabsorption will increase, and the amount of water excreted is going to decrease. Everybody follow that okay? Now, I threw this one in here because it involves what happens when you exercise and you sweat. So, you know, when you are engaged in intense exercise and you sweat a lot, you know, you're going to lose not only water, but you're also going to lose salt. So you are losing a dilute salt solution. This is going to trigger a decrease in your plasma volume. This will also trigger an increase in plasma osmolarity, because although you're losing salt, you're not losing a ton of it, but you are losing a lot of fluid, and so that's going to make your plasma a little more concentrated. The decrease in plasma volume will drive a decrease in GFR, which will also promote an increase in the release of plasma aldosterone. Now, let me tickle your brains a little bit here and see what you remember. Knowing that aldosterone is going up here, how's that aldosterone being signaled to increase? What is happening to cause that upregulation in aldosterone? And the key here is we've got a decrease in GFR. So what's the relationship between these two? Go ahead, Andrew.
The macula densa cells are sensing less GFR, and so then they're communicating to the juxtamedullary.
And what's being released? Renin. Okay. So renin, through a series of steps, and we'll actually look at those again, is actually promoting the increase in aldosterone. So what does that mean for GFR? What's going to happen what's going to happen in response to this decrease in GFR, because you know you're not going to want to keep that GFR down, right? What's the Renin also going to do? I'm just testing your brains here a little bit, helping you remember this, because who knows, it may even show up on a test. Go ahead.
It's also gonna lead the release of angiotensin 2, which is gonna increase GFR by increasing.
And specifically, how does it do that?
Increases blood pressure.
And specifically, how does it do that? What's angiotensin do? That's the hard one, huh? What does it promote? Go ahead. Where? If you have to raise GFR, there's only one place that can happen. Efferent, yeah. Yeah, so angiotensin 2 will promote vasoconstriction of the efferent arteriole, which will raise GFR. That's correct. Okay, and so that's all that's going on. That's all that's going on here. This will also promote, as you know, we saw in these two flow charts over here, an upregulation of plasma ADH/vasopressin. So the loss of the fluids is increasing plasma osmolarity here due to the decrease in water concentration. Both of these promote an upregulation of ADH/vasopressin, which will promote water reabsorption. Okay, decrease water excretion. The aldosterone, circling back to this because I forgot to mention it, also will reduce sodium excretion, because remember, aldosterone promotes the reuptake of sodium, so that you will not, over excrete sodium, since you're already losing some of it in your sweat. So I put this up here just so you can see there are a lot of things that are interacting going on here in order to maintain your homeostatic state with regard to both water and salt. Questions? Did all of that make sense? Oh.
Sorry. I thought about it. Would you be able to explain again why the plasma aldosterone increases and GFR decreases?
Well, GFR decreases because you've decreased your fluid volume in circulation, and so that's going to drop your blood pressure, and so that will drop GFR, and the kidney will respond to that. You're going to get that release of renin, which will upregulate angiotensin 2, which will vasoconstrict the efferent arteriole and the glomerulus, which will get GFR back up, because that'll increase the pressure in the glomerulus. And then renin also promotes the release of aldosterone, which is going to cause you to reabsorb sodium.
Okay, yeah, that makes sense. Thank you.
Okay. Anything else? All right. So we mentioned aquaporin proteins. I thought we would take just a moment to just kind of review. There are 4 aquaporins that we have dealt with regard to kidney function. The most common one, and this is aquaporin 1. Aquaporin 1 is found in virtually all cells. Okay, and it is a water channel that is always active. In the kidney, you're going to find it in both the luminal and basolateral membranes of the proximal tubule and those portions of the loop of Henle that are permeable to water. So the descending arm of the loop of Henle, that is going to be the job of aquaporin 1. It's probably been one of the most studied of all aquaporins because it was the first one that was discovered, which is why it's called aquaporin 1. Okay. Aquaporin 2, as we mentioned, is a very specific aquaporin found in the luminal membrane of the collecting duct, and its density is dependent on your blood levels of ADH. Aquaporin 3, as we saw, is another aquaporin that is always active, and it is located in the basolateral membranes of the late distal tubule and the collecting ducts, and again is responsible for constant water permeability of those membranes. So these are never taken out of the membranes like aquaporin 2 is, and similarly aquaporin 4 seems to be confined specifically to the collecting duct. Okay, but it is also found in the basolateral membrane and contributes to the constant water permeability of those membranes. And so those are the 4 aquaporins that are primarily involved in water transport in the kidney. All right. We can't get through a topic without having some sort of calculation, right? So we got to have a calculation. One of the ways in which we can look at the effectiveness of the kidney in clearing a particular substance is by calculating what's called renal clearance. All right. And renal clearance, by definition, is the amount of a substance cleared from plasma per unit time. And the simplified version of the equation is down here. The excretion of a substance is equal to the amount filtered minus the amount reabsorbed plus the amount secreted. So you've got a certain amount that's going to be filtered through the glomerulus. You've got a certain amount that's going to be reabsorbed and set back into circulation. You've got a certain amount that may be secreted back into the nephron, and then what's there after that is going to be excreted in urine. Okay, and that's simply how you calculate renal clearance, is to account for all of these things. This is the equation. If you are working off of a downloaded version of the PowerPoint, note the change in page number here in Hill. Renal clearance is equal to the urine concentration of whatever substance you're interested in times the urine volume that is being produced divided by the plasma concentration of whatever substance you are interested in. Okay. This equation can be found in Hill, and actually where you're going to find it is in the box extension, which is something you actually have to go to the web for, or you'll find it on page 495 in the Widmeyer text. Okay, but anyway, it's a pretty simple calculation. Here's an example. So we want to calculate renal clearance for creatinine. All right, so we have the urine concentration is 6 milligrams per mil. We have urine volume production is 0.0833 mils per minute, and the plasma levels 0.1 milligrams per mil. So 6 times 0.0833 divided by 0.1, that works out to be a clearance rate of 5 milligrams per minute. So what this means is you are basically urinating out 5 milligrams of creatinine per minute. That's how much you're putting into the urine that you're going to excrete. So not a real difficult concept. You guys get this okay? Okay. All right. So I know you've all been dying to know how can we calculate GFR? You all been dying to know that, right? Okay, well, I'm going to give you one way to calculate GFR. You know, a common way to do this is to look at a substance, to look at clearance of a substance that is neither reabsorbed nor secreted. So you know that what goes through the glomerulus is going to come out in your pee. And one such substance is a substance called inulin. Okay. Inulin is, you will filter it at the glomerulus, but you're not going to reabsorb or secrete it. So whatever you filter is going to come out. And so all you really need to know is the plasma level of inulin, which you can collect via a blood sample. And you need to know what the urine concentration is of the inulin, which you can measure just by collecting urine. Right? So in this particular case, we have a plasma concentration of 4 milligrams per liter. Okay, and that's the plasma amount. We know that all of that is being filtered. We know that that we are putting 30 milligrams of inulin into urine per hour. And so all we have to do to calculate GFR is divide 30 by 4, and we calculate our GFR, which is 7.5 liters per hour. Simple as that. It's not a real difficult thing to do. Did that make sense, everybody? Anita?
Yeah. It just confused me because I was like, why is it backwards? Like, but no, it's good.
I was just teasing you right now, so.
It's okay.
Okay. All right, so we've talked a lot about water. We've been mentioning electrolytes, but kidneys are very important in regulating electrolytes. When we first started this topic, we mentioned that pretty much all the sodium and potassium that's filtered is going to be reabsorbed because you use that physiologically for a lot of different things. And most of it's going to be reabsorbed before it ever gets out of the loop of Henle, and then we fine-tune when we get to the proximal tubule and collecting ducts. We've talked about how aldosterone is this interesting hormone that kind of plays tug of war with sodium and potassium, because if you have no aldosterone that's being produced, then you will pass a whole bunch of sodium, like 30 grams of sodium per day. But if aldosterone is being maximally secreted, you won't pass any sodium. You will reabsorb every little bit of it. On the flip side of this, remember that if you are reabsorbing all of your sodium, you're also dumping a whole bunch of potassium, because remember, aldosterone, when it's high, you're reclaiming a lot of sodium, but you're also secreting potassium at the same time. Okay. And the interesting thing about this is the amount of potassium that you would actually excrete when you are maximally producing aldosterone is going to be 50 times what you actually filter. So you are going to be pulling additional potassium out of circulation beyond just at the glomerulus, and dumping that into urine if you are producing a whole bunch of aldosterone. Now, clearly, this would not be a really good thing, because there are a whole lot of systems that wouldn't work very well without potassium, including things like your nerves, so and your muscles. So that wouldn't be a good thing. So how your body regulates aldosterone is really pretty important. Aldosterone is a key hormone, though, because it is a major regulator of blood pressure. And that's just because it's controlling the amount of sodium that's going to be in circulation. And as we mentioned earlier, sodium is the primary osmotic driver in circulation. And it really controls how much, what the sodium levels are going to be in the blood. Aldosterone is controlled by negative feedback. And actually what's driving this negative feedback are going to be plasma levels of potassium. Here is another one of these flow charts. I put this one in here because it reviews several different things and helps us to kind of understand how, you know, where renal autoregulation fits into a lot of these processes. So you have plasma volume decreasing. And then this is going to kick off a whole bunch of things. It's going to increase sympathetic activity. And by the way, if you are using a version of PowerPoint, this star was in the wrong place, and I moved it to the right. I moved it to the right place here. So just take note of that. It's going to activate sympathetic nerves. And remember, last time we looked at how the ways in which sympathetic activity actually interfaced with the kidney. It's going to decrease arterial pressure, which is going to elicit a myogenic response. It's going to decrease GFR, and so tubular glomerular feedback. Wow, that is a mouthful. Is going to get activated here. All right. And so this will reduce sodium flow to the macula densa. All of this is going to result in the juxtamedular cells upregulating renin secretion. Plasma renin goes up. Plasma angiotensin 2 is going to go up. The adrenal cortex is going to upregulate aldosterone in response to that. So plasma aldosterone is going to go up. Then you are going to get an increase in sodium reabsorption. But the byproduct of this, and this is one of the main reasons why I stuck this flow chart in here, the byproduct of that reabsorption of sodium is that water will follow. Okay. So water will follow the sodium because the sodium is creating a gradient, an osmotic gradient for the water to be reabsorbed as well. And so both sodium and water excretion are going to decrease in this scenario. Does that make sense to everybody? All right. So the last thing that I want to talk about with regard to nephron activity is how it is involved in the regulation of pH. And it's involved in the regulation of pH at several points as filtrate moves through the nephron. And so we'll start in the proximal tubule. And in the proximal tubule, what happens is that pH regulation starts here because hydrogen ions are going to be secreted into the filtrate in the proximal tubule. All right. So here you have hydrogen ions that are being secreted, and they're being secreted via an exchanger, a sodium exchanger right here. So it's going to pull sodium out of the proximal tubule, and the hydrogen ions are going to be secreted in, and then the sodium potassium ATPase will reclaim that sodium. So this is part of the process of the reabsorption of a lot of the sodium in the proximal tubule, but here we're getting the dumping of these hydrogen ions, and we pointed that out when we did our quick walkthrough of the nephron. Okay, and so then that hydrogen will combine with a bicarbonate to form carbonic acid, which will then meander its way through the nephron. Okay, so in the proximal tubule, we start pH regulation by secreting hydrogen ions into the filtrate. All right, then when we get to the distal tubule, not a lot of this going on in the loop of Henle, but then we get to the distal tubule. then what happens is that carbonic acid that was produced up in the proximal tubule will then be broken down by carbonic anhydrase into just water and CO2. Then this bicarbonate is going to be recovered. So the water and the CO2 actually will be moved back into the cells of the distal tubule right here. Then it will be back converted. It will be back converted into a carbonic acid, which will dissociate into its ions. The bicarbonate is going to be recovered here, and then the hydrogen ions will again be secreted out into the filtrate. Okay, so it's kind of a complex sort of thing that goes on here. There's a lot of carbonic anhydrase that is in the filtrate, so it's going to break down the carbonic acid to water and CO2. Those will be absorbed into the cell, back calculated or back converted into bicarbonic anhydrase into carbonic acid, and then the bicarbonate will be recovered for the purposes of buffering your blood, and then the hydrogen will be dumped back into the filtrate. And then finally, and I will finish. Oh, I'm over time. Okay, I'll do this on Monday. Okay. I will come back and revisit this total slide because I hate to leave something partially done. We come back on Monday. Questions? Everybody have a great Thanksgiving.
Two.